In this video, we're going to take a look at the fundamental theorem of calculus part 2. So in previous videos, we looked at the fundamental theorem of calculus part 1, and we saw that essentially the derivative of this integral function gets back to the original function we're taking the integral of. And then we use that fact to do a couple of examples in a more recent video. But now, what are we actually trying to do with this definite integral? We are trying to find the area under the curve if the function is a positive function on the interval. But we're trying to find the area under the curve between some x equals a to x equals b value. And we haven't done that yet. We haven't gotten a nice way to do that yet. And that's where the fundamental theorem of calculus part 2 comes in. This takes our fundamental theorem of calculus, and now we can apply that to make use of the idea that the derivative of the integral goes back to the original function. So here is how we are going to do that. Well, first we'll just state the fundamental theorem of calculus part 2. And that is that if f is continuous at every point in this closed interval a to b, and capital F is any antiderivative of this function f on the closed interval a to b, then our definite integral from a to b of f of x dx is just the antiderivative evaluated at b minus the antiderivative evaluated at a. And that is our fundamental theorem of calculus part 2, and it also significantly reduces the hassle that we will have when trying to calculate this definite integral. This is generally much simpler to do than the limit of that summation that we had created several videos ago as our definition of the definite integral. So, let's go ahead and prove this. We never proved the fundamental theorem of calculus part 1, but we can use that to prove part 2. And so what can we say here? Well, the fundamental theorem of calculus part 1 tells us that an antiderivative exists, so g of x is equal to the integral from a to x of f of t dt. All right. Then, if capital F is any antiderivative of f, then capital F of x is equal to g of x plus some constant c for x in the interval a to b, in the open interval a to b. And it turns out also, since f and g are continuous, on the closed interval a to b, then we get that capital F of x is equal to g of x plus that constant c. This holds on the endpoints x equals a and x equals b. So, let's go ahead and evaluate the right-hand side then of this formula up here. Evaluating f of b minus f of a, we have f of b minus f of a is equal to g of b plus c minus g of a plus some constant c, which is just g of b minus g of a. But what was that? Well, this was, as we defined it, right? g of x is just the integral, the definite integral from a to x of f of t dt. So this tells us that g of b is the integral from a to b of f of t dt, minus g of a is the integral from a to a of f of t dt. But what is the integral from a to a, right? That's just 0. So in fact, f of b minus f of a was just equal to the integral from a to b of f of t dt. And that's exactly what our, shouldn't have circled all of that, that's exactly what our fundamental theorem of calculus part 2 says. There it is. Sorry, that line was not supposed to be there. The integral, the definite integral from a to b of f of t dt is equal to capital F of b minus capital F of a, where again capital F is any antiderivative of this lowercase function f, the function we're taking the integral of. All right, let's go ahead and do 2 examples, and that will finish out this video. We're going to solve the following definite integrals. Let's solve the integral from 0 to pi of cosine of theta d theta. To do this, we need an antiderivative of cosine of theta. So the derivative of sine is cosine. So the antiderivative of cosine is sine of theta. And we just need the any antiderivative of cosine of theta. So we can just use the antiderivative sine of theta plus 0. And now here's our notation. We usually put the second half of a square bracket, and we say that we evaluate from 0 to pi. So that's just our notation on what to do now. And what is this? This is sine of pi minus sine of 0. So we just evaluate our function at the second value, pi, and we subtract off evaluating that function at the first value, 0. So we get sine of pi minus sine of 0. What is sine of pi? That is 0. What is sine of 0? That is also 0. So in fact, this integral is 0. Let's think about that. Does that actually make sense? What is our definite integral from 0 to pi of cosine? Well, our cosine function from 0 to pi looks like this. That is the first half of the period of the cosine function. And if we're taking the integral from 0 here to pi, or theta is equal to pi, and this was theta is equal to 0, then this definite integral should be this area here plus this area here. But reminder that the area below is a negative and the area above is a positive. And because of what we know about this cosine function, we know that the area in here is equal to that. So in fact, the definite integral is a1 minus a2, but those are equivalent, so we should get 0. And that's exactly what we calculated here using our fundamental theorem of calculus part 2. Okay, let's do one more example here. Let's find the integral from 1 to 4 of the function 3/2 root x minus 4 over x squared dx. So what we need to do is we need to find an antiderivative of this. All right? So this is x to the 1/2. To find an antiderivative of x to the 1/2, we first add 1 to the exponent, so it's x to the 3/2. And then we divide by that new exponent. So 3/2 here divided by that new exponent 3/2, well, it's just 1. So this is 1x to the 3/2 is the antiderivative of 3/2 root x. Now we need the antiderivative of negative 4 over x squared. Well, here we had negative 4. This is negative 4x to the negative second. So what do? We raise our x to now 1 higher power, so it's negative 1. And then we divide by the negative 1 exponent. That's going to turn this into a positive 4 out in front. And we evaluate this from 1 to 4. I can rewrite this just to put it in notation that we're a little more comfortable with. 4 over x, evaluated from 1 to 4. And then we do our calculation, which is we evaluate this function at the second value, 4. So we have 4 raised to the 3/2 plus 4 over 4. And we subtract off this evaluated at 1. So that is 1 raised to the 3/2 plus 4 over 1. All right, 4 to the 3/2 is 8 plus 1 here, minus quantity 1 plus 4. So we get 9 minus 5, which is 4. So we get 4 as our definite integral from 1 to 4 of 3/2 root x minus 4 over x squared dx. And that's where we'll end this video.